Hey everyone, I hope you all are safe and doing good. So now you know what is DP, what is dynamic programming. The overview, I guess, at least you know. And we use DP technique to solve problems. It's an optimization technique. When the problem has two conditions or two properties or two characteristics, which is overlapping subproblems and optimal substructure. Then we can use DP to solve that kind of problem. What is overlapping subproblem we have discussed, and what is this optimal substructure that also, uh, I guess you know. With the help of this Fibonacci series, we I have shown you that this problem is DP. We can solve this with DP because it is having both these characteristics. Overlapping subproblems means small problems are repeated multiple times and solved multiple times. So that is overlapping subproblems. Optimal structure. Yes, just find out optimal solution of subproblems and this will give you optimal solution of that main problem. Means optimal result of the subproblems to achieve a optimal solution of the bigger problem. Means, or in another way you can say, if the bigger problem has optimal solution, then for sure all the subproblems which are there in this bigger problem have definitely optimal solutions. So yeah, subproblems are this and this. So I get optimal solution for F5, optimal solution for F4, and I'll combine this and you will get optimal solution for the bigger problem. So this is a DP problem. Okay. But now the thing is, there are two ways to implement dynamic programming. Yes, there are two ways, two techniques. First is top down approach. Second is bottom up approach. Very first, we'll see top down. Top down approach. In this approach, we use recursion plus memoization. That's why I've told you in the previous lecture, recursion is prerequisite for DP. So I hope that you know recursion. Plus, what is memoization? That also I'll show you. So first, let's understand this top-down approach. In this, we are having few steps. So first step is we take the bigger problem. We look at the bigger problem like we are going to find F6. So that is bigger problem. Just break this into smaller, simpler sub-problems whenever required, whenever needed. So we need it because we can't solve this. So we just do what? You know the formula, na? So I'll simply draw that recursive tree. F5 and F4. Yes, the formula is, recursive formula is that Fn is equal to f of n minus 1 plus f of n minus 2. Yes, Fibonacci of n. Now, we are using recursion, so this will be called, I guess you know these, that program also. If I write the program here, see, we write the recursive method. So we simply check if we know if n is equal to 0, then it will simply return 0. And if n is equal to 1, then it will return 1. These are base cases because when you are writing recursion, then it's important to find out the correct base cases. So these are base cases. Otherwise, if it is not the case, then what we return? We simply return, we just call fib of n minus 1 plus fib of n minus 2. Yeah, this was the program. We have discussed this. Okay. So I'm just taking this simple example to get you a little bit more familiar with the DP. After this lecture, we'll solve DP problems. Okay. We return that. So now fib 9. Now n is sorry 6. So this condition not true, this condition not true. Now return with again recursive call fib of n minus 1, that is F5 and F4. But first recursive call is this, so it will be expanded. This recursive call will be calculated once we go back. So it's f of now again 4 and 3. Now for this f of 3 and 2. Now for this f of 2 and 1, like this recursively. For f of 2, it's f of 1 and f of 0. Now f of 1. Now whenever we call this for f of 1, so this condition will be true and it will return 1. So it will return 1. 1. But after that, we call this. One right is still remaining. So it's like 1 plus f of 0. F of 0 will give you 0. It will return 0. So it will be 1 plus 0. That is 1. So now it is 1. So now it will return 1. But right is still remaining. So f of 1. We again call f of 1. This is 1, so it will return 1. So 1 plus 1, 2. So this will return 2. So right is C. Now right is again f of 2. So again f of 2 will be called f of 2. N is 2. So this not true, this is not true. Now f of n minus 1 will be called. That is f of 1. Or we write something like this. F of 1 and f of 0. Again f of 1 will be called this condition true. So it will return 1, it will return 0. So 1 plus 0, that is 1. Now 2 plus 1, that is 3. So it will return 3. F of 4 will be 3. So 3 will be returned here. Yes, like this happen. But right call f of 3. Okay, again it will be expanded. So f of 2, f of 2, f of 1. F of 2 again expanded. F of 1, f of 0. It will turn 1, 0. So it will be 1. It will be 1. So it will be 2. 1 plus 1, that is 2. 3 plus 2, that is 5. It will return 5, but this f of 4 will be again be expanded. So f of 4 will again expanded. That is f of 3 and f of 2. F of 3 will be f of 2 and f of 1. F of 2 will be 1 and 0. Then is 2 will be again 1 and 0. Like this, normal recursion happens. Like this is normal recursion. But the thing is, again, I have told you that we are calculating this f of 2 multiple times. Here also, here also, here also. F of 3 multiple times. Here, here, here. F of 4 also multiple times. Here, here. So it is kind of right now, we are not using any DP. Right now, if I ask you time complexity means how many recursive calls are there? Time complexity of a recursive function, how you calculate? Number of recursive call into time taken per recursive call. So time taken per recursive call means how many recursive calls are there basically? See, f of 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I guess 25. I'm not sure, but around 25. For just f of 6, if n is 6, see, when n is 6, recursive call are almost 25. Like this, when n is 10, it will be 177. When n becomes 20, these recursive calls are almost 20,000. So these recursive calls are increasing like exponentially. So it's 2 raised to power n. Time complexity will be approximately like 2 raised to power n. That is definitely not good. Whenever you go for n larger n, if you write n is equal to 100, so see, it will take more time to give you correct result because it's really slow. Recursive call will be 2 raised to power 100. So see, you can imagine how many recursive call will be there. Or maybe sometimes you will get stack overflow error also. Because now, can we optimize it? Yes. It is overlapping. It is having those overlapping subproblems and optimal substructure. So what we do is, whenever we solve this, like f1 is 1, this is 0. So I get now f of 2, 1. So I will store somewhere. That it's somewhere. I don't know where, but for now, somewhere I will store. For this 2, whenever we have 2 as a parameter, then the value is 1. Now we get 1. Now f1 is 1. So f of 3 also we get. So whenever parameter is 3, then the value is 2. Now I go back. Now f4 has been calculated. So now whenever the parameter we pass is 4, then value is 3. So I store it. Now again, when parameter is 5, the value is 5. So like this, I'm storing somewhere. So what I do is, whenever after coming here, I go to f of 2. So I check first here, wherever you have stored these values, whether you have the calculated value for the subproblem f of 2. Yes, f of 2, it's 1. So directly here I will put 1. There is no need to call for this one. There is no need for this recursive call. Directly 1 will be using. Yes. Now next, whenever I go at right side, f of 3, first check where you have stored this f of 3. Is there the value you have calculated or computed before? Yes, I have calculated it. I have solved this previously. The value is 2. So why to expand this? Why to call f2 and like that? No, don't do this. Just use this value, that is f of 3 is equal to 2. Just use 2. It will become 5. Now whenever you go at this side, now f of 4, you check here. Do you have For f of 4 value, calculated value, yes, I have 3. So do not call this. Just put here 3. Just use it 3 and it will be 8. That's it. See, so how many recursive call? Do you need to call this? No, it's gone. Do you need to call for this? No, it's gone. Do you need to call for this? No, it's gone. So how many recursive call for f of 6? Just 1, 2, 3, 4, 5, 6, 7, 8. I guess 8. Previously it was 25. So drastically it will reduce number of calls. Maybe 8 or 7. In the program when we write, we can calculate it. So maybe it's 8 or 7 around. Yes. So it's almost n. N is 8, so n is 6, so it's 8. So n plus 1 or n plus 2, but we ignore that. So number of recursive call will be n itself. That's it. So time complexity is order of n. Previously it was order of n 2 raised to power n. See, we have decreased it from this to this. This is what DP. This is what top down approach. We are using recursion plus. Now the values we are storing, this is known as memoization. Yes. So it's like we break the complex problem into simpler subproblem whenever required. Find the optimal solution to these subproblems. Store the result of these subproblems, and this step is known as memoization. Okay. Now we can reuse this result whenever we need, so that we don't need to compute the subproblems again and again. Now finally calculates the result of the complex problem. These are simple steps. So that is first approach, top down approach. Right? Now can you modify this a little bit? This was with the help of normal recursion. Now add DP here. How to update it? See. So what I do is, see, after calculating, we were simply returning that. So once we calculate this, like this will return f 1, 0, we calculate plus of this and we return. Okay. Now 1 is calculated here for f of 2. So we simply return this 1. But before returning, we store it somewhere. So what we can do? It's like we can make a table. So it's kind of table, but in a table, generally we have number of rows, number of columns. Here, do you need such kind of thing? No, because only one parameter we are passing, that is n. N is 6. So we go from 0, 1, 2, 3, 4, 5 till 6. So we can only take single array, 1D array. Yes. So just take a 1D array. Somewhere we need table as well. Whatever the n size, sorry, n plus 1 size. So that the index can be 3, 4, 5, 6. Because we need to store for everything the calculated value. So it's 0 to 6. F is also 6. So sorry, the n is also 6. So total size will be n plus 1, that is 7. So we take a array. Okay, initially suppose everywhere it's minus 1, minus 1, minus 1, minus 1. Now what we do? Whenever we return from here 1, so before returning at f of 2, just store the value, calculate value, that is 1. So just make it 1. Now it is done. Now a 2 is returned. Now it will return 1. So this will be 2 plus 1, that is, sorry, it is 1. For f of 2, it's 1. So 1 plus 1, that is 2. It will return 2. So f of 3 will return 2. But before returning here, we will store 2. Now, before returning, f of 4 will become 3. So before returning f of 4, at the place of 4, n is 4. So at the index 4, we store 3. We store 3. F of 5, the value is 5. So for 5, it's 5. Now for 6, it's 8. Like this we store. So how to check this? How to store it? So before returning, what we do? We just take somewhere array. Suppose array is DP. Array DP I have taken. So what I do is, before returning, what I do? Just change DP of n. At nth index, just store whatever the value is and then return this DP, whatever the value n. That's one case. That's one step. But now see, whenever we go here at right hand side, but f2 is already calculated, na? So no need to call. No need to call recursively. It's already calculated. So we just fetch the value 1 from here and just use it. So that also you need to write, you need to update in the code. Where to write? After checking this base case, what I do is, Before this, I will simply write if dp of n at this array at nth index, if it is not equal to minus 1. If it is not equal to minus 1 means there is some value. So no need to call recursively, just return that value. Just return dp of n. Simple. If this value is minus 1, still minus 1, yeah, you call recursively, because at starting everyone is minus 1, minus 1, minus 1. So at least you have to call 1 till here, at least. After that, it's computed and then you will get some values. So there, if it is not minus 1, just return that value. This is how you will modify it. That's we have used here dp to solve this recursion, this Fibonacci series problem. In this case, you can just count number of calls will be really less. So it will make the program faster. Then normal recursion. So basically, DP is kind of, we are optimizing the recursion. It is optimization recursion. So we are optimizing the recursion here. This is top-down approach. Time complexity, space complexity. For this time complexity, order of n, because we are simply calling for this one, it's constant, we are calling this, so we don't change it. So per method is constant, but number of calls are what? How many calls are there? Almost n calls are there that we have seen. So it's order of n for this. Yeah, space complexity, when we use dp, we are taking extra dp array. So space complexity is order of n for this dp array, this array, extra array you are taking for storing the result, and n is for recursion stack, because we are using recursion. So recursion can also go in deep. How many frames at a time can be there? N frames. So n for that. So n plus n, order of n plus n. This is space complexity for this. Order of n is time complexity. Okay. So let's code this out first. Then you will get it. It's working or not. So what we do is, first we write like, suppose int n is equal to whatever n is 5, and we pass. We take a method only fib, and we are passing here n, the value n, plus, okay, only n we are passing. And whatever it will return, we just print this. Let's define this method. If n is 0 or n is 1, simply return n, otherwise return. Recursively we call fib of n minus 1 plus fib of n minus 2. Return that. At last, simply n. So n is 5. Let's run this, and it's without dp, just with normal recursion. So n is 5. It will return what is 5? It's 5 only, because the series is it. Obviously, it is not printing the series, because we are returning only the that fib number in that series, the number at 5 for 5. So it's 0, 1, 1, then 2, then 3, then it will be 5. Then for 6, it should return 8. So if I change n is equal to 6, it will give me 8. At that, it's 8. So yeah, it's 8. It's working. If I show you number of calls, so let's take one variable int count is equal to at first. Let's make it only count. Now, whenever we call, we just increase this count variable count plus plus. Okay. And at last, we simply print this count variable also. Number of recursive call and plus count. So for 6, when n is 6, number of recursive call, I guess it was 25. Number of recursive call 25. When n is 10, number of recursive call will be 177. See, 177. If you increase this to 20, it's almost 20k, 20,000 or 21,000. So see, 21,000 almost, 21,891. See the recursive calls. So it's tough. If suppose I write here 100, so it will take time. It will not work. See, let me show you. See, it's not printing anything. Na? So you can wait for some time and check out. But I'm just terminating it here. Now I want to reduce number of calls. So what I do is just add a touch of DP here. Just use that memoization. Okay. So what I'll do, what we can do is, let's take an array here. Int, let's make it DP array or memo array or any name you can take. New int and n+1 size. With n+1 size and with fib of n we are passing this array as well, DP. So here as a parameter you need to write DP as well. You're passing this DP. Now we do one thing. Okay, just count plus plus. And after this, let's do one thing. I will check if DP of n. Okay, you have to fill it with -1 else also. So let's write arrays dot fill the arrays DP with -1. Just fill it with -1. Okay, import this class also. Import class with arrays class. Now, if it is -1 equal to, okay, not -1, it's not -1, means we have computed that. So simply return from this array itself DP of and whatever the value. Otherwise, don't directly return. Calculate this first, store that value at that index, and then return. And then return that value dpn. Okay. Now we are passing here two things. So rather than n+1 itself, just pass dp also and just pass dp array. Okay, here, comma, dp. And here, okay, sorry, the dp we are passing obviously n and dp. Like this you have to pass. Right? Close it. Now you will see if I go for n is equal to 6, it will print 8 plus the calls. Previously it was 25, but now recursive calls are only 11. Let's make it 10. 10. Let's run this again. Previously calls were 177. Now calls will be only 19. So almost you can say 2n kind of thing. So it's polynomial. Polynomial. Previously it was exponential. If I say it's 20, previously it was around 21,891. Now it's only 39. Number of recursive call only 39. For this n is equal to 20. So almost double. That's it. And if I write here now 100, see, let's see it works or not, or how much time it takes. N is equal to 100. See, obviously this is not int, cannot store that. But see, the recursive call are only 199 and you quickly get the result. Previously it was just working because of number of recursive calls. So it's 100, but that we can't store in some int value. So you have to make it double or kind of that, returning double long value or that thing. But yeah, that's the case. Okay. This is what top-down approach. Let's make it 6 again. I hope you get it. Now, if you're not getting it, it's okay. You can do one thing. You don't have to count. That is extra thing I'm doing. You just make it. Just to show you that, yeah, number of calls drastically decreased. That's true. It's not just that I'm telling you it's decreased, so it will be decreased. No, I've shown you that it has decreased number of recursive calls. So now you do one thing. You take example and dry run this code. Dry run this code. How this is working, how this is first stored in this DP array and then return that. Okay, I guess you can do it. That is first approach. Now let's modify the same problem with bottom-up approach. So in this case, what we were doing, we started with the bigger problem, and whenever we divide this into smaller. So that is kind of top-down approach. Top-down approach. But now bottom-up approach. Bottom-up means we start with smaller problems. We start with smallest problem or the base cases. Then we build the answer step by step. Then we move further. And we reach the final answer iteratively. So here we don't use recursion, it's iterative approach. We use loops. Same thing, we have to calculate fib of 6. What we know? Fib of 0 is equal to 0 and fib of 1 is equal to 1. We know these two things. So what we can do? Can we calculate fib of 2? Yes, fib of 2 means this plus this. So f of 1 plus f of 0. We use the same recursive formula, but not recursion actually we use, but the formula we use. Formula is simple addition, na? F of n is equal to f of n minus 1 plus f of n plus n minus 2. So that is 1, that is 0, it is 1. Now calculate f of 3. F of 3 will be f of 2 plus f of 1. We know f of 2 is what? 1. We have calculated this. So we store it somewhere in table. So it is known as tabulation also. So we use it. That is 1 plus 1. It will give me 2. Like this we solve. For f of 4, we know what we need. F of 3 plus f of 2. F of 3 you know? Yes, we have calculated. That is 2. 2 plus f of 2 you calculated? Yes, 1. So it will give me 3. So that is bottom up. We started with the smallest problem, the base cases. Then one by one we build the answer and we reach till finally f of 6. Like that. So can you update this thing rather than recursion? Just use iterative. It's really easy. Base cases we know. So what we do is, see, we'll do one thing. We will have a array, DP array. 0, 1, 2, 3, 4, 5 and 6. What we know right now? What we know? For 0 it's 0, for 1 it's 1. That thing we know. Maybe here we can keep it 0, 0, 0 or minus 1 you can put. These two things we know. So we just put these things in array at first. Okay. So we have a DP array. So we can put something like this. DP of 0 is equal to 0 and DP of 1 is equal to 1. We know this thing. Simple. Because that was the base cases. Base cases in that recursion also. We know this thing. These are base cases and recursion we have applied for these things till 2 to 6. So we can run a loop. We can run a loop here where I will be 2 to whatever n. From here we start the loop and 6. Step by step now we build. Now what will be here? At dp of I. So basically at right now this array name is dp. dp. At dp of 2. What will be, what we should store here? We just add this and this. Previous 2 we add. So whatever dp at 1 and whatever at 0 we add. So 1 plus 0 that is 1. So it will be 1. So here whatever at dp of I, what you do? Just add at I minus 1 plus I minus 2. Simple. In this loop. At last, now see when I is 2, so dp of 2 is 2 minus 1, 1 and 0, so it will be 1. Okay, next I plus plus, now I becomes 3. So when I is 3, so we add whatever dp at 2 and this, so it will be 2. When I becomes 4, then we add this and this, it becomes 3. When I becomes 5, we add this and this, that is 5. When I become 6, so yeah, it will run till n. We will add these two. When I become 7, stop. So at last, you simply return this. It is the answer. So we simply return after this loop whatever dp of n. N was 6, so whatever at 6, just return that. That's it. Simple. But yeah, you have to write one thing here. Suppose I give n is equal to 0, fib of 0. So it will do one thing. I will calculate an array, which is this dp int dp is equal to new int size will be n plus 1. Okay, what is n? That is 6, so it will be 7. So if n is 0, so it will create an array of size 1. Size 1 means only one index. But now I say dp of 0 is equal to 1 and dp of 1 is equal to 1, but there is no one index. So you will get array out of bound index. for this case, special case when n is 0. So you can handle this case separately. Whenever n is 0, so you just check if n is equal to 0, return 0. Because we know that when n is 0, so at first we have 0. So handle this case separately and then just continuously. You don't have to write if n is equal to 1, then also return 1. Because if n is 1, I pass. It's not true. So array will be calculated with size 2, 0 and 1. So we assign 0 here, 1 here. Loop will be from 2, but condition will not be true. So we'll be out from this loop and simply return dpn. N is 1, so it will give you 1. So that's fine. It will work. So see how easily we converted this recursive to simple iterative approach by using simple this one. So that is bottom up approach. We are using iteration here. We started with the smallest answer we have, smallest base cases we have, and we build the final answer. That is bottom up approach. Okay, same in this case also. Time complexity, we are running the loop from 2 to n, so it's almost order of n. Time complexity order of n for this. Space complexity, what extra thing we are taking? DP array, it's of size n plus 1, so it's order of n. Time complexity and space complexity. Previously it was n plus n. N was for recursion stack, and n was for DP array. But here there is no recursion stack, so we have done it. We optimized a little bit. Space complexity terms. In this term, it's order of n itself. But when you see deeply, then only 1n. Previously it was 2n. Time complexity is same. So here what we have done is, rather than using recursion, so see here also we were storing this data in some tabular form, but here we don't use any table because 1D array is fine. But still, it's like you can say tabulation kind of thing we are storing. We were filling this data. I've told you now, in DP DP generates data while solving the question, and at last picks the final or optimal result. So that's how we generates data. Okay, but it was with the help of this recursive tree, and then we fill it. But without recursion also, directly we can fill this table. We don't need recursion tree or recursion. We directly fill this table. So that is bottom up approach. That is known as tabulation. Okay. Now pause the video and you code this out. So we just do one thing. Just comment out this. Using top down we have done. Now let's. Second. Okay. So one thing, in this case we don't need to pass this DP. Okay. There's no recursive call. Within this only we do one thing. We can just take this DP array within this method definition. We don't need to pass DP here. Just pass only n, right? There's no recursive call. So okay, we have commented this out. Here also just leave it as it is. Or if you want to fill it with -1 at first, you can fill. Or no need to write down this thing. No need to fill. Let's leave it as it is. Initially it was 0, 0, 0 everywhere. Okay. And before this, we simply check one edge case. That is, if n is equal to 0, simply return 0. No need to do anything. But now it's not 0. Then we do what? At first we know two things. DP of 0 is equal to 0. We fill this array, and DP of 1 is equal to 1. These two were the base cases. We know this thing. Now we run our loop from 2 to less than equal to n and I plus plus. N is 6, so we equal to 6 till then we run. Now we calculate DP of I is equal to previous 2 we will add I minus 1 plus I minus 2. Simple. And after calculating, simply return DP at n, whatever the value is. That's it. So that is we have done with just bottom up approach with iterative. Let's run this and see. For 6, it should print 8. So it's 8. If you change it for like 5 or 8 or 7, it would be 13. And for this, it will be 13 plus what's 8? That is 21. 21. This is bottom up approach. Can you optimize it a little bit more in terms of space complexity? Space complexity, space should be constant. Can you do it? Pause the video and think about it. See, basically to solve this, we need two, at first only two things. Two, you can say values, 0 and 1. We just keep adding this and we are done. So rather than taking this array, we don't need. We just do one thing. We take a variable that is we are calculating this current, so we need previous values. So it's like previous values may be previous value 1, previous value 2. Rather than this, we just take 0 and 1. Now same, run the loop. We calculate rather than this I and all. Here we write previous 1 plus previous 2 is equal to whatever current value. Whatever current value. You get current value. So we have added 0 plus 1 and we get 1. So this is my current. Previous 1. So previous 1 is equal to 0. Previous 1 is 0. Previous 2 is equal to 1. And my current is equal to 1. Now to find out next value when I becomes 2 and 3. So to get this value, what we need? Just previous two values. Just previous two values. Why we are storing all this? To get this value, just previous two values. To get this value, just previous two values I need. So why I'm storing all these values? No need. Just two previous values you have to store. So at first, this was my previous one. This is my previous two and this is my current. Now I want this one. Next. So I becomes 3, this one. So I will just shift my previous 2 here. This will become my previous 2 and this becomes my previous 1. That's it. So after calculating it, just shift it. Just shift it. Here I will simply write that thing here. I will change my previous 2 is equal to current. Whatever the current was, that becomes my previous 2. And previous 1 is equal to previous 2. Whatever previous 2, that becomes my previous 1. These 3 steps you need to write, and at last just simply return. Because at last, now this will be calculated. Just added these two. So now my current is this. Now I becomes 4. So to calculate this value, my previous 2 becomes this. My previous 1 becomes this. We calculate this. This is my current. So we get 3. Now I becomes 5. Next I becomes 5 plus plus. So this becomes my P2. This becomes P1. And this is my current. I get it. Now change it. This becomes my P2. Next. And this becomes my P1. This is my current. After this, current 6. Okay, get. Now we change. So when I was 6, that condition is true. So we calculate this. Control will enter here and all these lines will be executed. After calculating, this becomes my P2. This becomes my P1. When I become 7, loop, that's it. At last, whatever we return, whatever previous 2 value, that we return. Whatever previous 2. That's it. We are not taking any array. We are just taking 2 variables. So in this case, yeah, time complexity is because we are running the loop from almost 2 to n. So it's n, but space complexity for this case is constant, order of 1. So we optimize this a little bit more in terms of space complexity. So the question may be asked in interview. Can you optimize it more in terms of space complexity? Yes, we can do it. Pause the video and code this out. So I'll update this a little bit. Here also, here only I'll update. Don't take this DP array. Rather than this DP, this, let's comment this out. I will take 2 variables. V1 is equal to 0. and prev2 is equal to 1. Loop will be same. Comment out this. What I do? Calculate current. So let's make it int current. Now my current is prev1 plus prev2. Now I'll change previous one and previous two. So I will move prev2 is equal to current and prev1 is equal to now prev2. Uh, yeah, there is one thing. We have to do this thing. So previously, see, previously prev1 is 0, so it was 0. Prev2 is 1 and current becomes 1. So current becomes 1. This is my current, this is my previous 2, this is my previous 1. Previous 1 is 0. So this should be my previous 1, this should be previous 2. So at first, if you move, previous 2 is equal to current. Okay. So now this one becomes my previous 2. Fine. But now previous 2 is equal to previous 1. So previous 2 is now this one. This previous 1 also becomes 1. Means same thing. You will not get it for now. See, let me show you one more thing. Now, for next, it becomes 1 plus 1, that is 2. When I becomes 3, so condition is true. So previous 1 is 1, previous 2 is 1. So current becomes 2. Okay, fine. Now current becomes 2. See, understand it. Now I'll change current is equal to previous 2. So current was 2. So now my previous 2 is this 2. So now my previous 2 becomes 2. Prev 2 is equal to 2. Right? After this assignment. Now next statement is I am assigning now my prev1 is equal to prev2. So what is prev2 right now? 2. Previous 1 will also become 2. Both are same. That should not be a case. Previous 2 should be 2. Previous 1 should be 1. Okay. So you can't write in this order. You have to first change this. Control X. So first change previous 1. Okay. Right now my current is 2. Previous 1 is 1. Previous 2 is this one. First change previous 1. Now my previous 1 becomes whatever my previous 2. Previous 2 is this one. So now my previous 1 becomes 1. And now I'll change previous 2. Now my previous 2 is equal to current. Current is 2. So this becomes 2. Now that's fine. Now next time when I becomes what? When I becomes 4. So when I becomes 4, condition true, yes. Now current is equal to pre1 plus pre2. Pre1 is 1, this is 2, so that is 3. That's exactly I want. 2 plus 1, that is 3. So now my current becomes 3. Okay. Now I have to change. This should be my previous 2, this should be my previous 1. So first I will change my previous 1. Don't write that first change this and then change this. It doesn't matter. No, it matters. Okay. So you have to make this order. This is the correct order to write down these two statements. That's the mistake generally students do. They write previous 2 is equal to current first, then this. They think that, okay, both are same line we are writing, so order doesn't matter. It matters in programming. And at last, simply return what is prev2. That's it. Run this. So for 8, what should it give? It's 21. Okay. For 6, it was 8, I guess. No? So it should give me 8. So yeah, it's working. So in this case, space complexity is constant. You try this out now yourself. If you're not getting it, just try run this with more examples. So we solve this problem Fibonacci series problem with 3 approaches. Basically 2 DP approaches. First is this, second is this. For this, time complexity, space complexity is this. For bottom up, it's order of n, only one n, and then we optimize a little bit based on space complexity. Now, one question generally students ask is factorial. They are getting confused. Is factorial a DP problem? You pause the video and think about this. Is it a DP problem? We calculate suppose 5 factorial. What it will be? 5 into 4 into 3 into 2 into 1, or I can write 5 into 4 factorial. So if you know 4 factorial, you can put it here. Yes. Or I can write 5 into 4 into 3 factorial, like that. Is it DP problem? No, it's like n into factorial of n minus 1, like this. Factorial of n minus 1. Factorial n minus 1 is same n into factorial n minus 1. So are the sub problems overlapping? Main problem is 5 factorial. Sub problem is we are calculating 4 factorial. There is no overlap. There is no overlapping sub problems. That same problems we are calculating again and again, like in Fibonacci series. So this is not, it's not necessary to apply here DP. Without DP, we can solve it simple recursion. Okay, so that's not a DP problem. It is not having overlapping sub problems, right? Now you know DP, you know approaches of DP. Now in the next lecture, we will be solving some questions on dynamic programming. So now I'll see you in the next lecture. Till then, bye bye. Take care.